Alright, welcome back. Section 5.6. We're finishing up Chapter 5 with some exponential growth and decay models. We're going to use these when we talk about radioactive decay, when we talk about half-life that we saw back in pre-calculus and some of your science courses. Also with population growth or anytime we're talking about money growing. So we've seen a couple formulas. We're going to bring this back from pre-calculus, y equals ce to the kt. We're also going to relate it to that a equals pe to the rt. So we just change that variable y and a, doesn't really matter there. So that's our final amount. Our p was our principal. Well, when we talk about c is going to be how much we initially started with, our initial population, if you wish. And we have our e, and then this r and k. So remember this r, this was our interest rate that we were talking about. That's how it grew. This k is going to be our k is going to be a constant. It's going to be either a growth or a decay constant, depending on whether the population is growing or if it's dying. So a couple things can happen with k here. K can be greater than 0, it's going to be a growth, and if it's less than 0, it's going to be a decay. And then we talked about c and our y values. So things that you're going to have to do, if you like steps, we're going to find the k value first. We're going to rewrite the equation and we're going to solve the problem. So most of these are going to be two-step problems. The first step is going to be finding that k value. So here's what we saw last year and in subsequent years there, or previous years. Carbon-14 is a radioactive isotope of carbon. It has a half-life of 5,715 years, give or take. So it depends on what book you use, depends on what the radioactive half-life is for carbon. So I've seen anywhere from 5715, 5700, up to 5740. So you have to be very careful when you're working with these to make sure your k value goes along with the number of years. Anyway, if 100 grams of carbon are initially present, find the amount present after 10,500 years. So the first thing we're going to do is we're going to go ahead and set up to find our k value. And to find our k value, we're going to start with that y equals ce to the kt. And in order to find that k value, we know the half-life of carbon-14. So we know that if we start with 100 grams, then in 5,715 years, 15 years, after it goes by, we're going to be left with 50 grams. And we can continue this on and so forth. So it doesn't matter what we start with, we're always going to end with half of what we started with. So if we end, we can say we end with 50 grams if we started with 100 grams. These two numbers are going to be very arbitrary for us. As long as this is half of this value here, what we start with, we're going to be able to find that k value. And our k value, or our t, our time, is going to be the half-life of 5,715 years. So this tells us that if we start with 100 grams, after 5,715 years, we're going to end with 50 grams. We're going to go ahead and solve then for k. So I'm going to divide by my 100, and I'm going to get 1/2. And we're going to find that it doesn't matter what we start with and what we end with, we'll always have that ratio or that fraction of 1/2 at this point in time. So if you want to always start your k values at that point for half-life problems, you're by all means able to do that. How can we go ahead and solve now for k? Well, I can go ahead and take the natural log of 1/2 equals the natural log of e to that exponent. I can bring this exponent to the front. So 5,715k times the natural log of e. And we know the natural log of e is 1. So I have the natural log of 1/2 equals 5715k. I can go ahead and divide by my 5,715. And I'm going to pull out my calculator here. Oh, I guess I saw it earlier there. Oh, well. So we have the natural log. There we go. Natural log of 1/2. And I'm going to divide that by my 5,715, which is my half-life here. Oh, I hit something wrong. What did I hit wrong? Oh, I hit divide twice. So natural log of 1/2, I'm going to clear that out. Natural log of 1/2 divided by 5715. Hit something wrong there. So I get this negative 1.212, blah, 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 e to the negative fourth. Remember, e there means times 10 to this exponent. I'm going to go ahead and store this value so I know what my k value is. So k is negative 1.212 times 10 to the negative fourth. So remember to store, I'm going to go down here right above the on button is the STO, and I'm going to hit my alpha, and then math is going to give me my a. So that's going to store my a value there. All right, now we can go ahead and answer this question. So I know my k value, so I know that y is going to equal CE to the negative 1.212 times 10 to the negative fourth t. We want to know, well, if we start with 100 grams, how much is going to be present after 10,500 years? So we're going to start with that 100, so we have y equals 100 e to negative 1.212 times 10 to the negative fourth times the number of years that have gone by, which is 10,500. So now it becomes a calculator problem. All I do is put this in. I know this here is my k value. So if I put in 100, my e value, so my second natural log is going to be my e. I'm going to put my k value, which is my alpha a, and then times 10,500. Go ahead and hit enter, and I'm going to end up with y equals 27.985, and that's going to be grams. And that should hopefully make a little bit of sense to us. If we think about the half-life of 5715, after one set we're going to have 50 grams if we start it with 100. If we then at the end of the second time we'll have 50, or at the beginning of the second we'll have 50 grams. After another 5,715 years we're going to end up with 25 grams. If I add those two half-lives together, I have about two half-lives there, or about 10,000, roughly 10,000 years have gone by. So after about 10,000 years, 10,400 years, I'll have 25 grams. Well, here, 10,500 years, I had 27.98 grams, didn't I? All right, so very close in that manner. Here's another one that we like to look at. Skeletal remains on Earth contain 20% of the carbon-14 they originally contained. How long ago did the person die? Oh, poor guy. So what do we know? Well, again, we know it's an exponential growth, or decay. And in this case, we know it's a decay because it's only having 20%. So how much did we start with? Do we know how much we start with? And the problem here, it doesn't say that we know, so we can go ahead and make up any value we want. Say maybe we start with 100 grams, like we did before. We can start with 50 grams. But we know if we start with 100 grams, we're going to have 20% of what they originally contained. So I'm going to end up with a 20% of the material. And that's e to the k times t. In this case, since we're working with carbon-14, we already know that k value, and I've stored it in my calculator. So if you already have it in your calculator, you have it stored, you're good to go. If not, we can find that k value just like we did before. So I'm going to go ahead and solve this. I'm going to divide by my 100, so I get 0.2 equals e to the k, which is that a value, times t. Remember that a I stored in my calculator. I can go ahead and take the natural log of both sides. And natural log of e again is going to go to 1. So I use a times t, and I'm going to divide by my a. So I can go ahead in my calculator, do the natural log of 0.2, divided by my alpha a. And that's going to give me 13,269.819 years. So that's approximately how old or how long ago this person was that died way back then. In our next problem, we're going to change up our K value. So we have a radium-226, a half-life of 1599 years. Determine the initial amount if after 10,000 years there remains 2 grams. So again, we can go ahead and find our K value. We're going to start with y equals CE to the KT. Again, we don't know how much we started with, so we can start with whatever we want as long as we end with half of it to find that K value. So 50, maybe we start with 100 again. K times the half-life is 1599. So again, we're finding that K value first. Again, see we have that 1/2 is going to be our ratio e to the 1599K. So in my calculator, I'm going to do my natural log of 1/2. Since I'm going to take, I guess I should go ahead and show that. Natural log of 1/2 equals 1599K. Natural log of e again goes to 1. I'm going to divide by 1599. So the natural log of 1/2 divided by my half-life of 1599, and that gives me a K value of about negative 4.334 times 10 to the negative 4th. Again, I'm going to go ahead and store that. Since I'm working with these, I stored my carbon-14 as A. I'm going to go ahead and store this one as B. So if I have another problem that I had to work with, carbon-14, I know in my mind, hey, I've already stored that as A. If you overwrite it, doesn't matter. You can go back and find it later. All right, so we can go ahead now and answer the question. So the question is, if after 10,000 years, so we know that our T value is 10,000, and we know that we had 2 grams remain, so we want the initial amount. We know what that C value is. So we have that K, which is now our B, times 10,000. So in our calculator, kind of pretty much becomes a calculator question. We can go ahead and divide by that B times 10,000, and divide by E to the B times 10,000. So we're going to take 2 divided by our E to the B, so our alpha B, times 10,000. And that's going to give us an answer of 152.631 grams. And that's going to how much we started with. Alright, and I have one last problem. It goes to the money problem. Determine the amount of money in an account if $1,000 is invested for 10 years at 6% interest compounded continuously. So we saw this one way back in the beginnings of Chapter 5. It kind of comes back in our exponential growth and decays as well. So here we know that K value is 6%. So we're going to start with $1,000, and we're going to invest it at 6%, 0.06, and then we're going to go for 10 years. So again, we throw it into a calculator. We're going to end up with 1,000 times our E to the 0.06 times 10. And that's going to give us $1,822.12 in our account. So that gives you an idea of where we're going to see half-life and some of our problems with half-life, and with our exponential growth and decay, some of our population growth, and our money. So good luck, enjoy. If you have questions, let me know.